Experiments conducted in a lunar gravity environment have the potential for impactful discoveries that can both advance our understanding of the Moon and improve life on Earth. Currently, researchers conducting lunar gravity experiments in space are faced with large project costs and long project durations. The same NASA team that developed Strata 1 and Hermes for microgravity research on the ISS has been approved to develop a new research payload which will fly aboard a Blue Origin suborbital flight in Q1 of 2023. Our team, Sub Orbital Astromaterial Research, or SOAR, has been subcontracted by T-Star, a local space commercialization company, to develop a fully functional research payload for NASA. Our system will be capable of hosting 4 independent experiments, which can be uniquely configured prior to the flight. By utilizing flight-proven hardware from NASA, our project timeline and development costs will be greatly reduced, allowing us to provide a cost-effective solution to NASA in a more reasonable time frame. Now let's meet the project team.
Howdy, I'm Michael Townsend and I'm the project manager for SOAR. I'm tasked with overseeing the successful completion of all aspects of our project, as well as designing the mounting interface for connecting the components of our system to the Blue Origin locker.
Howdy, my name is Kevin Leonard and I'm the hardware engineer for SOAR. I'm responsible for designing, developing, and implementing the printed circuit board, which will allow for power distribution to the devices in our system.
Howdy, I am Ryan Labarbera and I am the software engineer for SOAR. My main responsibilities include creating the software for configuring experiment control and integrating flight signals from Blue Origin with our devices.
Howdy, my name is Kersch-Hamar and I'm the systems integration and test engineer for SOAR. I am responsible for verifying that the SOAR system meets payload requirements set forth by Blue Origin, as well as testing to ensure that all systems meet the standards set forth in the functional requirements and performance specifications.
Hi, I'm Kristen John. I'm the Technical Integration Manager for Lunar Dust Mitigation for the Space Technology Mission Directorate at NASA.
Our conceptual block diagram shows the process that the New Shepard system follows from liftoff to landing. It begins with the New Shepard lifting off from Van Horn, Texas. When it reaches about the Kármán line, which is about 100 kilometers above the Earth, the crew capsule will separate from the main booster and rotate at about 11 rotations per minute to induce the localized lunar gravity. At that point, our research payload will begin experimentation and actively record data for several minutes of the experienced lunar gravity, after which the crew capsule will return below the Kármán line and begin its landing procedures. The SOAR research payload will be housed in a single locker aboard the crew capsule shown at the top center of the diagram, from which we will receive 27 volts nominal power and data in the form of flight events through the IPC, the Integrated Payload Controller, which is our interface to the crew capsule. The power received from the IPC will first go through a fuse and then into our custom bird board, which will convert and regulate the power before it is distributed to the rest of our system. Each experiment channel will feature a BeagleBone Black for the intelligence board, 2 cameras with different angled lenses, diffuse lighting to indirectly illuminate the experiment canisters, and a PWM controlled entrapolator, which can compress and release the astromaterials inside the canister. Picture data from the 2 canisters along with sensor data from the 4 sensors and load cell will be collected and stored locally for post-flight analysis. Each experiment channel will also feature a battery-powered real-time clock for time-stamping data and a 9-degree of freedom sensor to record flight telemetry. All of this will be included in 1 experiment channel, and the SOAR system will feature a total of 4 experiment channels, each made independently as to limit any potential for a single point of failure and to allow for unique configurations.
Here you can see a full view of the New Shepard suborbital flight system. The booster and crew capsule will begin the flight attached to one another. However, once the flight reaches the Kármán line, the crew capsule will separate from the booster and rotate at 11 rotations per minute. This will cause a centripetal force vector radially inward, which will result in a sensed acceleration radially outward. Inside the crew capsule are 6 payload stacks. Each payload stack houses the equivalent of 6 single lockers, such as the one containing our research payload. You'll notice that since this locker was stored on the left side of the payload stack, it has the IPC interface on its left side. Every locker, regardless of left or right orientation, has an opening on the front and top sides for loading and unloading the contents of the locker. Opening the top of this locker reveals the layout of the SOAR system. The SOAR system is designed symmetrically to allow for flexibility between left and right orientation use, as well as to keep the center of mass as centralized as possible. The design is kept very modular, allowing for a simple installation into the locker. All 4 experiment canisters are raised by mounting supports to create a pocket of space running along the bottom of the system for the bird board and intelligence boards to have easy access to all components with minimal wiring. The cameras are configured in such a way that they will capture pictures from both sides of all 4 experiment canisters, providing plenty of image data for researchers. The image and sensor data collected during experimentation in a lunar gravity environment using the SOAR system will provide NASA researchers with valuable insights into the dust settling and granular mechanic behaviors of astromaterials in lunar gravity.
So as we return to the moon with the Artemis program, it is critical that we understand what the lunar regolith, sometimes called lunar dust, does on the lunar surface and how it behaves. And so one of the best ways that we can do this is by studying the behavior of the regolith in the lunar gravity. And we can do this via Blue Origin's New Shepard flight. And so we have this awesome opportunity to actually have 2 minutes of lunar gravity. And by working with the SOAR capstone team at A&M, we're actually able to build upon an existing ISS experiment to study the dynamics of these particles.
We would like to thank our project sponsor, Professor Matt Leonard, President of T-STAR, and our technical advisor, Dr. Joseph Morgan. We'd also like to give special thanks to the Principal Investigator for the project, Dr. Kristen John from NASA, as well as Mr. Victor Yu, a NASA engineer assisting us on this project. Thank you for your time. If you have any questions regarding our project, please contact us at soar.tamu@gmail.com or through our website linked below.